Good morning. So, you know the topic, right? Tert-amino effect, and this was covered last year. Maybe for some of you it would be partly repetition, not all of it. Okay, for those who are not exposed to this, will have something pretty new in this sense that nitrogen has a special effect, especially when it is a tertiary amine. Okay. So, today's topic would be Tert-amino effect, and some people say Tert-amino effect reaction. Okay, that means this effect has been converted to reactions, and the reactions have been very useful in synthesizing fused heterocycles. And along with that, we will also talk about a little bit of these oxygen heterocycles and some miscellaneous or the variant of the original Tert-amino effects. For example, towards the end of the class, we will have something like this, and let us say if you have an acyclic compound and react this with BF3 ether and with ethylene glycol, and the solvent is methylene chloride, and the temperature is around 50 degrees centigrade and certain hours, let us say in this case 12 hours. So, you should be able to predict the reaction of the product. Probably towards the end of the class, we will see whether we can predict the reactions of these or rather reaction products. Okay. And what is the meaning of it? The meaning of it meaning of it is that it must have a benzene ring, and then it must also have a tertiary amino group, and this should be ortho substituted with a double bond. If you simply heat it, that means the reaction conditions are very mild. In one sense, there is no complications. There are no in terms of the use of the reagents or no sophisticated reagent. What you will find? You will find a cyclic product, and which will be looking like this. This is A and BH. This is one of the products. The other product could be also product could be say 6-membered ring system, and with hydrogen attached to nitrogen, and then nitrogen and these other things. So, what you see here, a single reaction can produce imidazole derivative as well as the pyrazine derivative. And take an example, a precise example, then what you will see, and concrete example could be, let us say take this one, and I will just switch over these, let us say double bond on the top, maybe top, and then E. E in our case, let us say stands for ester, and then now this tertiary amine is part of a pyrazine ring system, and the reaction conditions, you need a solvent. This solvent is normally little high boiling solvent, high boiling polar or non-polar. Okay. Non-polar solvent high boiling is toluene. Okay. So, around that temperature, and polar solvent like alcohol also refluxes. What is it solvent? Butanol. So, just simply butanol, what you will find in this case, that means there are two possibilities on the top, 5-member and 6-member. In this case, what you will find? You will find a reactions which will give a 6-member compound, and the the structures could be written quite easily, and if you follow these common reactions given on the top, and here is E and here is E. Okay. So, what is the mechanism? What is the mechanism? The mechanism could be you can what I can just write in terms of the simplify this. Let us say this is E, means electron withdrawing group, the double bond and nitrogen here, and there is what I said is a tertiary amine. That means these two should be alkylated, and the tertiary amine should be such that there should be an alpha hydrogen. That is the important thing. When I say tertiary amine, actually tertiary hydrogen should be alpha to the nitrogen, there must be a hydrogen here. Okay. And what is expected, that there would be sort of a resonating structures of this kind. So, a double bond here and then E, and now sort of a kind of a Juiter anion, and then this is a cycle. Don't write anything about that. Okay. So, what next? This is what you have to find out, that all of us know there is the possibility of sigmatropic rearrangement, 1,5 sigmatropic rearrangement. That is a possibility. I mean there is no common consensus about the mechanism. I mean all kinds of mechanisms have been proposed. One of the mechanisms is that 1,5 sigmatropic shift is possible at this stage. There are other ways of looking at this by internal hydride transfer. Okay. But the one that is, let us say, so what you do here is just do an intramolecular hydrogen transfer and giving this is E and negative charge here, and the hydrogen is picked up, there is a double bond nitrogen, and now what you see that double bond has been shifted, shifted. Rewrite this. So, what you will find, okay, so hydrogen has been shifted, these esters diester contains a negative charge the alpha position, the nitrogen, and now you have a iminium ion here, which is equivalent to, if you rewrite, it is equivalent to, see all you can see there is just a carbon ion sitting next to the iminium ion, and obviously the possible reactions that one can say see the neutralization of the positive charge on nitrogen. So, eventually what you could find a, what is that, basically a cyclization process, or you can say annulation process, this is a fused heterocycles, and where the backbone is an quinoline derivative, it is a quinoline derivative, and you have these two ester groups. So, this is one of the, that means what in learning this sort of reactions, what you have to learn, you have to do the prerequisite, or what are the structural prerequisites. It is a benzene ring, and it should have an carbon-carbon double bond and ortho to the carbon-carbon double bond, or it could be an tertiary amine group with an alpha hydrogens. That is what you have to remember. Okay. Then let us say I have one more, I mean quite a few examples. That means the examples where is here, what do you see? Again a benzene derivative, and it does not have to be a carbon-carbon double bond now, you see. It could be a simple multiple bond, Now, the reaction condition either heat or light depending on the situation here. In this case what you will see, just the light. So, what do you expect? Yeah, hydrogen transfer, basically hydrogen transfer. It could be through the 1,5 sigmatropic sheet, or it could be through the direct internal hydride transfer. And in this case, there are possibilities, but the hydrogen, all of us know in photochemistry, hydrogen normally is transferred to oxygen, right, and then this is iminium ion is formed, and this nitrogen is negative charge now. So, result is of course, result is now is somewhat different. Now, what is it? It is an imidazole derivative, N-hydroxy imidazole derivative, N-hydroxy imidazole derivative. So, likewise you can also expect very similar kind of reactions, and what we do in our lab also kind of if you take a quinone and photolyze it. So, so what you see here, I mean this is not exactly the aromatic system, but it has a tertiary amine, it is an alpha hydrogen. So, if you photolyze it, all of us know this, the carbonyl would be excited, and this sort of radical is generated, and then you will have 1, 2, 3, 4, 5, 6. So, you will have a 6-member transition state. You can just straight away you can this hydrogen transfer can take place, right, and or but in this case what you will see, if hydrogen is transferred to carbon here, oxygen minus, and this iminium ion. Okay. So, essential driving force for this sort of reactions is the formation of the iminium ion, and then thermodynamic stability of the final product. I mean, one can write also the hydrotransfer to the oxygen. Okay, but had it been the radical reactions, probably that could have been a possibility. And so, once you have these, then what is expected? So, 1, 2, 3, 4, 5. So, you have a 5-membered now, 5-membered ring system, and another 5-membered ring system with a bridgehead nitrogen, and the quinone. Now, all of us know what is the next phase. Next phase is basically the aromatization, and this 5-membered etc., and this OH and this. So, that means what basically, if you can recognize a tertiary amine structural component and little bit of pi systems here and there, then under very mild conditions you can. So, this is just example that it does not have to have a carbon-carbon double bond, polarized, it could be carbon oxygen double bond nitro. And then other examples, for example, the next one, what you will find again a tertiary amine. So, throughout you will see the tertiary amine, towards the end we will switch over to something little different, and then this group here, okay, and let us say this is something, okay. So, and the reaction condition simply heat in a solvent, either tertiary butanol or toluene. So, what do you expect? And what do we expect? Normally, what is the functional group here? Tertiary amine group and the nitrogen, double bonded nitrogen. The name of the functional group? Azo group. Okay, azo group is only undergoes cleavage and the let us say photochemical isomerizations, but in this case it is a thermal reaction. And but since you have a tertiary amine group with an alpha hydrogen, so you can do all kinds of mechanism, either as a 6-membered form. That means in almost all of these reactions, what we will be talking about, the reaction takes place alpha to the nitrogen. That is one of the commonalities throughout this lecture today. Okay. So, that means one of these bonds will form at this carbon, and it could either form on at this nitrogen or this nitrogen, that is it. Okay. And normally the 5 member 6 member formation is governed by the thermodynamic stability, and if you have 2 nitrogen, imidazole formations is more likelihood. So, you have hydrogen here, mentally you can mentally I think it is better to just think about hydrate transfer internally, that is better. You can do this original that reaction mechanism where you can do little bit of these deuterium formations, then 1,5 sigmatropic sheet and then cyclization, and alternatively you can think about this hydrate transfer. So, if the hydrate transfer takes place, for simplicity's sake, maybe hydrate is transferred to this nitrogen here, and then you will have this iminium ion here, and this on this side you have this nitrogen, right. So, if this is positive charge, then one of these carbon must be or nitrogen must be negative. So, this is negative, and of course, then the end result is now an imidazole. So, annullated imidazole, and in this case you have nitrogen, that ring and NH and this methyl group here. Okay. So, what else do you expect under the thermal conditions? In heterocyclic chemistry, this is one of the very common reactions, like if you have a thermal reactions, you will find this nitrogen remains as it is, this nitrogen, this imidazole nitrogen remain as it is, then you have the other cyclic portion. What else do you expect from these amines? Actually, these amines also is a good leaving group under thermal conditions, and so it this methylamine is lost. So, eventually you get the formation of imidazole. Okay. So, what did we see so far? We have given 3 different examples. In all this is an imidazole, this is a sort of an oxazole, this is an imidazole. Okay, that means, whenever you have 2 heteroatoms, there is a likelihood that it would form a 5 membered ring system. Now, let us take one more example, where you have only carbon bonds. Once again, so pyrrolidine group, and in this case is a carbon bond. Reaction conditions are same. Reaction conditions are same as like heat and a solvent, and so what would you expect? Well, one thing what we can expect, that it first forms this iminium ion, right, and then you have to decide actually whether this hydride would be transferred to this carbon or the other carbon. Okay. And mechanistically, if the hydride transfer is required, that means it should go to the electron deficient, and trifluoroacetic methyl group is a electron deficient, right. But in this case, this I mean the carbon attached to this phenyl group should be electron deficient, because TF3 is electron withdrawing, right. But answer is a different one, and so in this case this hydride is added to the end of the trifluoromethyl group, and then phenyl gets the negative charge. Now, there is a possibility that the phenyl probably, this negative charge is probably conjugated to the phenyl, and so eventually that so end product is again a quinoline derivative. It is a quinoline derivative, and now you see there is a phenyl substituted quinoline derivative, and then you have all kinds of things here. And then there are questions about the stereochemistry here. Normally you get cis and trans, very occasionally you will get a pure product in this. Okay. And so that means one thing we can say that if you have two different kinds of heteroatoms, there is a likelihood that 5-membered ring would be formed, but there are cases where without the presence of heteroatom in the double bond site, you can also expect a 5-membered ring formation. I mean, it is somewhat tough to explain, why. Like say in the next example, we will see although you have a carbon-carbon double bond, there is a formation of the 5-membered ring systems. In all of the examples, what you see is a pyrrolidine, that is easy to form, again heat, and this is a toluene. So, I mean, now to begin with, we can straightway write the formation of this iminium ion, then hydride would be shifted. That is what we have to decide in this case. And the hydride, I thought the hydride would be which one would be hydride shift? Hydride, either this position is little exposed. So, there is a possibility that hydride, because it forms an anion here alpha to this cyano. If the hydride is added to this, this is also. So, I mean since I know the answer, I should I say that the product is a 5-membered ring, but from my experience what I can say that sometimes the hydride addition takes place from the less hindered side. So, if the hydride is shifted here, that means shifted to the cyano without a substituent, that means you get the carbanion formation here next to the benzene ring. So, the product is right, this is Cn, and now this is Cn, and of course, this other one is another 5-membered ring system, but mind it, you have two different groups, hydrogen and cyano. So, there are other isomer, and you can cis and trans. That means, in this reaction both the isomers are formed, both are formed. Okay. But then again there is no explanation why. There is, if you just change the solvent to butanol, only the cis isomer is formed, only the cis isomer exclusively is formed. Again it is not explainable, Okay. So, this is just a case where you have a carbon-carbon double bond, you can just convert it into the 5-membered ring systems. And this in the next example what I will show is it could be extended to Coumarin kind of molecules, where the lactone is very sensitive to most of the reaction conditions, since it is a thermal reactions. So, you can just simply carry out under thermal conditions even in the presence of weak acid to give a very complex molecule. This example starting from a Coumarin, all of us know, right, what is Coumarin? Coumarin is a bicyclic molecule with a lactone ring with oxygen attached to this phenyl ring, so it is lactone, and then the two functionalities that we have here is formyl group. Now, if you react this with ethyl cyanoformate, cyanoacetate, ethyl cyanoacetate, it should know, it is not, what is that? No, it is not ethyl cyanoacetate. What is that? Ethyl, what is the name of this compound? Ethyl cyanoacetate, fine, cyanoacetate, and then piperidine, all of us know it is a base, ethanol, And so, what is the what is the reaction? The reaction, what should be the reaction? Lactone can form, right? Lactone can open up. What else? It can undergo Knoevenagel reactions, right? See, all kinds of possibilities are there, but at this stage you are thinking it should be little mature, means in the sense that all these reactions are reversible reactions. So, you have to have a product which will not be reversibly going back to the starting material. So, the product is not the Knoevenagel reaction, the product is is a displacement of chlorine, displacement of the chlorine with this nitrogen, and now you have a formyl group here, Okay. What next? Now there is all of us know the chlorine, this piperidine is not a very strong living group. So, you can expect a Knoevenagel kind of reaction, and that is this one. So, double bonded now, and then at one side you have cyano, other side you have an ester which is E, and this is now piperidine. So, this compound is then actually in this case the solvent is acetic acid and is heated. So far we have been seeing that either toluene or butanols have been used, but in this case you have the acetic acid and just simply heat. Okay. So, what do you expect? So, we know now the requirements are fulfilled, that we have a double bond here, that means sort of Coumarin means benzenoids or benzene, and that means first thing what you have to recognize, this tertiary amine part and with an alpha hydrogen. So, that means if you can straight away write actually without thinking much, we can write that this backbone remains as it is, right, and then this tertiary amine parts remain as it is. Then we can blindly draw a bond here alpha to the nitrogen. It is then matter of forming a 5-membered ring or a 6-membered ring, that is it, because you have a polarized carbon-carbon double bond. Now, when we have a clean polarized double bond, we know what is going to happen, right. Hydride should be attached to the if this is let us say alpha carbon, this is the beta carbon, the polarization of the double bond is towards the cyano group. So, hydride should be shifted, that means one can write hydride is right here and the carbon ion forms there. So, it should be a 6-membered ring and this cyano and this ester. So, and we had one more hydride. So, this is how actually this compound has been actually verified by excess structure determination, and so they are all this is I think I will not bore you with other similar example. That means, it is a typical reactions of the chloroaldehydes. If you have a chloroaldehyde, the first thing that happens, that nitrogen displaces the halogen part. Okay. Then aldehyde goes on a vehicle. There are plenty of examples, and then under thermal conditions it goes so called the tertiary amino effect reaction. And now what? So, apparently everything is known. So, what else can you do? There are two mechanisms proposed. One is that 1,5 sigmatropic hydrogen shift, other is what I say internal hydride shift. So, which one do you like to accept? All these examples I showed till now can be explained in either of these mechanisms. Okay. One can quickly see that if it can be extended to macrocyclic compounds, where the 1,5 is not possible, something else which is less likely. Okay. Then we can propose that hydride shift could be a better mechanism, and that is what happened in next two examples. I will show that you can produce a macrocycle. Macrocycle means something which is bigger than 6, 7 maybe. Okay, that means 8 is considered to be a macrocycle. Like in this case, it is a biphenyl case. That means the backbone is a biphenyl. In the previous case, it was aromatic, right? And this is common, that pyrrolidine is common. We will see more example. This and then this gem dicyanoethylene component. Okay. Dicyano component. So, temperature is 100 degree centigrade with micro oven heating. So, what is the product? What is the product? You can do all kinds of things, nitrogen lone pair going through this benzene ring, when this thing, that thing, that eventually you get a deuterion, positive charge thing. But I think for us the easier is to view this reaction in terms of the internal hydride transfer. So, first we have to recognize that there is an alpha hydrogen, and this also nitrogen lone pair goes and hydride is shifted. So, if the hydride is shifted to this, so the backbone remains as it is, and then hydride is shifted to this place, then you will get a sort of a carbon here, right, this nitrogen and then iminium ion, and so apparently the reaction is very general, and under these conditions, so you will have 1, 2, 3, 4, 5, 6, 7, 8. So, you get a 8-membered ring system, 8-membered ring system. And we have nitrogen here, this 5-member, and this 2 substituent is a cyano. So, that means it is very general. That means one can use this for this construction of an 8-membered ring system. What else you can do? I mean, how to extend? Basically, at this stage, you have to think about how to extend this, or the changes, like many of you are the research scholars. So, you have to know how to change the reactions to or rather change the, or rather to include different kinds of examples. So far, we have seen this imidazole derivatives, this thing, that thing, nitroso, azo, all these compounds. Okay. In one case, we have seen the Coumarin, and so now carbon polarized. Now we have a macrocycle, and what is biphenyl systems. Now the next example actually is for, I think, 7-membered ring system, and so in this case it is a naphthalene case now. From naphthalene, if you want to like make a 7-membered ring, so what you can do? You can start with a disubstituted naphthylamine, and then treat this with butyl lithium and DMF. I think all of us know what is going to happen, right? What is going to happen? CHO, introduction of CHO. But they are at which position? It says 1, 2, 3, 4, 5, 6, 7, 8. Okay. 2 position, that is actually had it been methoxy, normally the reaction takes place at the 2 positions. Okay. But you have an option here, this is periposition. Actually, if you have lithiation, actually you get a 5-membered sort of a ring solution compound, and although yields are not good, but one can quickly make in one step and without much problem this, and then you can understand what we are going to do next, right? Do next. So, Knoevenagel condensation kind of thing with 2 cyano, which is very useful, very easy, and then this is this thing, this alkyl groups. So, you can have all kinds of alkyl groups, and then what the reaction condition? The reaction condition is heat, and in this case the solvent is DMSO and the temperature is around 100 degree in 4 hours. So, you get this reaction done, and this has been verified by deuterium leveling. That means, if you take the deuterated amine etc., you get this nice deuterium transfer, and eventually what you will find is the product will contain a 7 member ring, 1 2 3 4 5 6 7. So, okay, I think it's a 7 member ring, 3 4 5 6 7. Okay. So, 7 member ring, and this would be nitrogen. So, you will have, and this one should be cyano, this one should be cyano, and then you will have this one group here, methyl group here. Okay. So, that means these 2 examples will tell you that it is possible to make a macrocycles, and it does not have to follow the 1,5 sigma tropic shift. So, in intramolecular hydride shifts could be possible to generate the molecules here. And so, this reactions has been found to be quite general. So, we have general, actually there are quite a few examples. I think instead of the cyano you can take the ester, even let us say, that means I think the component could be here you have cyano. So, it could be even like say carbon here, carbon. So, like you can take a component where you will have these ninhydrin kind of molecule, and you can take a molecule of that meldrum acid, if you recall, meldrum acid 1,3-dicarbonyl compounds, and then diesters, all kinds of things here. So, I mean, so we have been, that means it is a very rather fairly general reaction. Now, what else can you do with this? Okay. Very recently, that means in 2009, this reactions has been utilized to fabricate a new antibacterial. Many of you know, right? And development of antibacterial is a very important field in medicinal chemistry. Why? Why? It's a continued process. Penicillin was discovered in 1940s. Tetracycline is discovered in 1948. Okay. So, then what is the next kind of antibacterial agents, antibiotics? We know penicillin, we know tetracycline. Then immediately after penicillin, actually something came called cephalosporin. Cephalosporin, what is it? 6 member ring. Good. So, we all know this. Then what is the latest antibiotic, latest class of antibiotic? Right, fluoxetines. Fluoxetines, actually best thing would be as an organic chemist, you should say quinolone derivatives. Fluoxetines are nothing but quinolone derivatives. Okay. So, then people are still struggling to come up with new kind of antibiotic. Reason being one, what is the reason? Resistance. This resistance. Okay. So, one of the drug candidate has a structure which nicely fits the tertiary amino group effects. Okay. The structure is like this. It is a quinoline. It is a quinoline kind of derivative, and the other portion has a morpholine kind of component, and on the top you will have a structure where you will have nitrogen in 1,3 position, and then it is sort of an urea, here, right. And I think my drawing is okay. Just you have to this is a methyl group here, and this is a methyl group here, this cis methyl group, and this hydrogen also cis here. There is a hydrogen here, is a cis, and okay. Let me. I think maybe should I rewrite? I think that would give you a better look maybe. Okay, quinoline portion, and then again a 6-membered ring, right. So, this is oxygen here. This I am just rewriting basically, and this just to show you the okay. And I think this one should be, let us say, flattened little bit. So, what you see here is an 1,3 dicarbonyl compound, then NH, and then NH here, and then you have a carbon. Okay. And this is a nitro group. This was, I mean, during a screening study, this was found to be a very active antibiotic. Okay. And this hydrogen is here, and this methyl group. So, all these hydrogen, this methyl and this methyl are cis to each other. So, how do you synthetically approach? That means, when you try to develop a synthesis, what is the first requirement actually? If you recall, during the retrosynthesis we talked about the, let us say you are given a task of synthesizing a molecule. So, what is the starting point? The starting point is to no, if let us say if you want to begin with a retrosynthesis, what is the first thing you start with? Functional group. Okay. This is very important. Wherever, if you let us say go to any kind of research topic, your starting must be very important. And all of us know a good beginning is half the battle. A good, so okay. So similarly, starting is a very important wherever you go. So in such a thing, actually, for a synthesis, the starting is to recognizing the structural pattern. That is important. And throughout organic chemistry, we have seen we deal with only very few things. What are the things? Whether how many cycles, how they are fused, and how many multiple bonds, and then how many heteroatoms. That is it, nothing else, and their interrelationships. So, and since this is a talk, it is a heteroatom basically. Heterocyclic chemistry means throughout the semester we have been talking about heterocyclic. So, what are the heterocycles? Then heteroatoms, nitrogen, etc. Their interrelationships. Okay, that means what I can see that when you have a benzene and this, so it is a quinoline system. Then you go to this large number of methods and for quinoline maybe I would say 100 different methods are there. Okay, and then you have a here morpholine moiety, fine. And to be little more precise, you can see a tertiary amine now, right. And what else do we see? We see something here. What is it? It has a common name, right? Barbiturates. So that's what you have to remember. That's it. Okay, and so how do you do? So now how do you break it? Okay, that means you break it here, right? So break it here, and what you will find, that means we have to somehow make this and NH, this is a carbonyl. This is a bad drawing though, but we are interested in. Then somehow you have to make this, that is it. So, we have recognized, that means this iminium ion should be there, and then this. Now, we know what to do. What next? This we have to, that this part remains as it is, that means somehow you have to make this barbiturate, and this part as you can guess, it should be something like this. So, this should be the most appropriate starting material, and okay. I mean now one can quick then what next? This double bond, carbon-carbon double bond is formed from the Knoevenagel reaction. So, the next one should be this aldehyde here, and then 6 membered this dimethyl morpholine, and I think all of us know this can be, I mean we are so used to these addition elimination reactions of Sanger's reagent. You have a nitro group up here. So, and if you begin with a fluorine substituent and aldehyde, so then this sort of thing should be pretty easy. Actually, what was tough to make this morpholine, we will not talk about it, but if you begin with this disubstituted morpholine here, NH, the reaction condition is quite simple, just triethylamine. So, you get to this compound. From here to here, obviously, what is the reagent? Nothing, absolutely no base is required. Urea is sufficiently basic, and just heating in methanol at 65 degree centigrade would give you the Knoevenagel product. What next? That means, you have to go to the tertiary amino effect reaction. There is one person has said that the reaction should be known as tertiary amino effect reaction. Well, it sounds odd, but this okay. Basically, you have to now do the ring closing reactions. What is the reaction conditions? The popular reaction condition is again, so I think from the temperature we can make out 117 degree. So, it is butanol. So, it is an N-butanol. Okay. So, then you get to this product, and this was published, see, very simple apparently, right, very simple, nothing, basically these sort of fluorocompounds are known, well known in the literature, and boiled with this morpholine in triethylamine, then just heating it in methanol with this corresponding barbiturate. This barbiturate means this one, NH, carbonyl, NH, this is readily available, all of us know, it is obtained from malonate and urea. So, so cheap, methanol is cheap, just simply heat it, then heat. I mean such a simple reaction, very simple reaction, and it was published in JACS. I do not know why, because it is too simple, and 991. Okay. Of course, there are some other things, and actually there is an interesting feature also. And probably I will not be able to tell you at the moment, but if I have the paper with me, if you can go to the original paper, what you will find, if you keep on heating in a different kind of solvent, this isomerization takes place in the methyl portion, methyl group. There is an possibly, I have forgotten, some isomerization takes place. That is also another aspect why the paper was accepted in JACS. So, what next? We have many examples actually. What next? We have seen tertiary amino effect for normal systems, then we have seen amino effects for the synthesis of making the macrocycles, then we have a typical sort of an antibiotic synthesis, and what else can you think of? You have to just change the structure, then must change the structure. For example, somebody has done it like this, X, and now the amine is a little different here. In all this previous example, nitrogen was attached to the phenyl ring. Now there is a CH2 here. So it is known as now homologous tertiary amino effect. Homologous tertiary amino effect. Okay. And what do you expect? Without going through the sigmatropic, all this shift, one would expect that hydride would be shifted to this, right. So that is, if that is so, then we C and this X and this C N hydride is attached to now this nitrogen here, and this iminium ion, right. So what do you get? You get the sort of Indian derivative. Indian derivative with X here, cyano, and this nitrogen and this one, and this is formed. This is formed. Okay. Then if you heat it, what do you expect? I think I will not write the mechanism, but all of you can guess. Sorry. So all of you can guess what will be the product. It is a 7-membered ring now. 7-membered ring with nitrogen and this, and X and C. Okay. So how is it happening? I think all of you can. I think you can write. You can do it. What is what you can do actually during this? There is also a possibility that this can undergo 1,3 kind of a sigmatropic, so 1,3 kind of a hydrogen shift, I should say, and this. That is it. So then it forms actually, and under certain condition it forms this. So we have more examples. I think we have more examples. So what else you can do? Let us say very recently in 2009 again in Jack's paper, what they did, instead of the carbon-carbon double bond, they just form the iminium salt. Okay, just a primary amine instead of the tertiary amine. They form, let us say, I mean these are the structural modification one can just think of, right. Let us say the nitrogen here, and if you take primary amine, so what you will find, you will have a imine base, right, and this was apparently very simple, but people have got to this kind of reactions. Then one more, I think I will tell you, I mean like say this is again a Jack's paper, again a Jack's paper. You take RCO, let us say R prime, and the reaction condition is nothing, just 10% benzoic acid, 10% benzoic acid, okay, 10% benzoic acid, and then it was heated in toluene. What do you expect? So pyroline, so 1, 2, 3 pyroline, and what do you expect? It is a new pyrol synthesis, or just you can sit down and do the mechanism very easily without any problem. This is the product. So again iminium salt is formed. Now internal hydride shift and transfer, and for these pyrolines, I think all of us know how to make these pyrolines, right? How to make these pyrolines can be made from this cis chloride with amine, and this is obtained from the corresponding acetylene and that butane 1,4-diol hydrogenated chloride formations and then this, or else okay, this is one of the ways to or else what you can do, even without using ammonia, you can use urea, close, but not okay. In this example actually somebody used urotropine. Urotropine is formaldehyde, ammonia, okay, that is urotropine. And then alternatively one can think about what is it? RCM. So, that means there are so many methods by which one can make this pyrroline, and these ketones are plenty in chemistry literature. Just mix them, hit them, you get the all different kinds of the substituted pyrrole derivatives. That is why it was published in JACS. Okay. And lastly I think probably we will talk about the first example. What was the first example? If you recall, first example, okay, what was it? I thought at the end we should be able to answer these questions. What is the product? What is the product? This one, first one. So, we know a lot about the tertiary amino effect, homologation, then the macrocyclic formations, all kinds of carbon-carbon double bond, carbon-carbon triple bonds, all things, but carbon-carbon triple bonds are missed though, maybe one day someone would do. Okay. I mean, so far I have not seen an example where hydride has been transferred to carbon-carbon triple bond. That is a nice research problem. Okay. And quick. This is again a very recent example. What can you think of? There is no nitrogen now, there is an oxygen, right, and the condition is that the butane 1,2-diol means like ketylation. Actually someone probably tried to do so, but eventually the product that they could get is a pyrene derivative with nice stereoselectivity is this, and this is the carbonyl of here, of course, this hydrogen indicated hydrogen has been shifted from where? This hydrogen. So, it is a secondary sort of, you can say, oxygen effect, you can say, that was tertiary amino effect and secondary ether effect. So, all of us know these oxonium ions are more stable, right. So, that would account for this sort of transformation, and there are plenty of examples. There are actually the literature that I mean, now this sort of reactions even without acid you can do, means by using simple DDQ. DDQ all of us know. One of the important reactivity of DDQ is that formation of an oxonium ion.